Hey, Quixeyers! Today we have a special treat. Our very own Eric Glover is going to talk to us about machine learning. Eric has worked at a lot of search companies. He has a PhD in search artificial intelligence, and he's finally decided to share all his search wisdom for us. So, Eric Glover, everybody.
So, I can't share all my search wisdom because that would be more than a 45-minute talk, but I can give you guys a basic primer of some kinds of machine learning, as well as share some interesting stories for those of us who already understand machine learning, and for those who don't, at least you walk away and have a basic idea of how to actually apply machine learning to real-world problems. So some examples of applied machine learning that many of us have experienced, you know, Netflix. If you've ever used Netflix, it makes recommendations. They use a kind of machine learning for that. Walmart will dynamically adjust its inventory in real time so that when you go to that store, everything that you want to buy is there. And they know, and they directly communicate with the factories in advance to make sure everything is ready. People might not agree with all the weather forecasts, but weather forecasting uses machine learning, voice recognition kinds of machine learning, spam filtering, and even like your airlines, when you fly, they try to maximize the use of these planes to keep prices low, and they can use machine learning to maximize that. Okay, next slide. So, wow, it's pretty cool stuff, right? So how do all these things work? Well, I'm not going to tell you how all those things work in this talk, because that's a different talk. But what I do hope this talk will accomplish is to help you to make better decisions as a human next time you try to apply machine learning. And if you don't understand the basics, at least you'll understand the basics of a specific type of machine learning. So, wow, that's a lot of stuff. You don't have to read it here because it's all from Wikipedia. But I'm going to focus on something called supervised machine learning, which is a very specific kind of machine learning. And simply put, it's you take examples of documents or pictures or whatever your input is, movies, and labels, and then you feed them into some magical black box which tries to learn a model to capture that, and that model can then predict the values of unlabeled examples. So maybe you have a movie that you like, and then you have a movie that you've never seen, and this model black box tries to predict how good it is. Although Netflix uses different algorithms and other things, the basic idea of supervised learning is you start off with labeled data, you run it through a learner, it learns a model, and then unlabeled data comes in and it predicts values. Okay? That's basically what this says. If you want, you can read the whole thing, or you go on Wikipedia. It's got excellent description. Okay, let's look at the next slide. So, the first thing you need to do in any supervised machine learning process, well, not the first thing, but one of the key stages is sort of this training stage, where training will take as input labeled data and produce a learned model. So in this case, we have a bunch of pictures of animals, and we have a label. We have a sheep, we have some cows, a pig, and some other, some other animals. And we want to kind of figure out what kind of animal this is. So let's start and let's build the models. So as you can see, the learner consumes the input and then produces a model. Okay? So that's machine learning, supervised learning in a nutshell, right? You take your input, label it, feed it into the model, you feed it into the learner, and you get a model. Okay.
You get deliciousness.
It's kind of like making sausage, right? You take all the input in, and then you get something out that's sort of an agglomeration of all the different inputs that you've got. So the idea is, you take your examples, you learn about the examples, and then when you see a different example that you have never seen before, this model will help you predict. So let's try to apply this model that we just learned to these animals. Okay? So now we have this model, and we want to take animals we haven't seen before and kind of predict what they are. So let's see what happens. So in comes this duck, and boom, hey, look, it thinks it's a duck with 90%. That's pretty good, right? The sheep comes in, and then it analyzes, and it thinks it's 50% cow. Kind of looks a little bit like a cow, so you might see why it made a mistake, but it's pretty good, right? Now here's a goat, okay? So a goat comes in, and it has no idea what it is, but it thinks it's a sheep cow, okay? But we didn't have any goats in the training set. Now here comes an octopus, okay? We've never seen any of those before. And it can't come up with anything. So it, in a sense, correctly identified as none of the above, okay? So in this simple example, they took the model that we learned, we put unlabeled data in, and then we kind of predicted what the labels are based on what we learned from the model. Okay? So let's go to the next slide. So let's talk about the actual process from beginning to end of building a supervised machine learner, right? The first thing you do, which sounds really easy, but it's actually the hardest part, is clearly defining your problem. And it's unbelievable how many times people will make a minor difference in the definition of the problem that make it from something that's nearly impossible to solve to something that's really easy to solve, right? And so that often people just think it's simple as, oh, I just want to identify animals, that's my problem. In reality, you should have a much more specific definition. Once you've defined your problem, now you want to sort of get to the formalization of this, right? You want to actually say, well, what are the inputs and outputs? What are the features that describe the examples? And what is the target that we're trying to learn? So maybe we're trying to say, okay, we have animals and we have features of these animals and we want to learn what the probability of it being each of these different sets of animals. So you get more formal and get more specific with your definition. The next thing is once you've got a definition, then you want to collect labeled training data, and hopefully for testing too, because you want to know how well you did. So you would take examples and get maybe a human labels them, maybe they are already labeled in nature, whatever it is, you collect your labeled data. Given your labeled data, now you need to convert these examples into a mathematical form, which I'm going to get into detail in a couple slides, but you're basically generating a vector of features. And for those who don't know what that is, I'll show you in a moment. But the idea is that you're actually building training data, which is just simply lists of features and what the desired goal is, and that goes and feeds into the learner so it can figure out to build a model. Once you've got that, you can run the model, run the learner to build a candidate model. Now you've got your candidate model, now you want to evaluate it. And unfortunately, very often things go wrong somewhere and your evaluation fails. And so if it's not good enough, then you may need to go back and repeat some of these steps. Maybe you realize your definition was bad. Maybe, instead of trying to identify 4 animals, you really want to identify 10 animals. Or maybe you want to break it down differently. Or maybe your features were just not correct. Or maybe you didn't have enough training data. Or you found errors in your training data. So any of these things can go wrong, and you're going to go back and retry them until you finally get something that works. And then when you're done, you can deploy the model to your real world. Okay? So there's 2 basic concepts that I talked about that I think are important to understand. One is the concept of features. I talked about this thing called features. So what are features? Features are properties of an example. They could be almost anything. So in the case of a web page, they could be things like a number of words in the document. Or if you're trying to build a search engine over apps, let's say, they could be the number of times the query word appeared in a review. Okay? Each query word. These could be features or properties of the world, of the example that you're trying to learn. Okay? And typically they're going to be numeric or Boolean, things that are easy for computers to process, although there are cases where they could be a string, like literally your input could be a word or a sequence of characters or the name of something. That's perfectly valid, although it's a lot more complicated for a computer to process those versus just simply 3.5 as opposed to some word. And so as an example, we can imagine for some learner, the first example, the feature vector is just 112 true orange minus 3.7, whatever that means, right? So each of these corresponds to a specific feature that has a very clear definition and basically to some clearly defined property. And the idea is that the features form a mathematical representation of each example. So you start with your example, maybe it's this picture of a duck or whatever, and then you end up with just some vector of properties and numbers, and that's where you kind of start applying the learner. The learner doesn't just look at a picture of a duck and say, oh, I think it's a duck. It looks at the features that you give it, and that's how the system works. Okay, let's go look at the next slide. Next, we're going to talk about models. Okay. So I talked about this idea of what is a model, right? So basically, simply put, a model in this world, and again, for those who are experts in machine learning, I'm oversimplifying a lot, but just trying to kind of explain in simple terms, a model could be thought of, especially for supervised learning, as just a simple function that takes as input a set of features, or actually a vector of features, and returns a value. So you could have a simple model that just says, if feature 1 plus feature 2 is greater than 3, then return true. or some simple function, or a very complicated model that involves weird, trigonometric functions and all kinds of other things that are beyond the scope of this talk. So the target value is just some function. No, that's good. You can go to the next one. It's okay. So I'm going to give you an example to kind of explain, in simple terms, what a model might look like. Again, typical kinds of machine learners may have much more complicated models or different models, but this is sort of a simple way to understand what's going on. So here, hopefully you guys can see, there's this grid, or this square. And inside this square is a bunch of labeled data. A minus indicates a negative labeled point. A positive is a positive point. So maybe in this case, we're trying to classify to predict if any given point based on its x and y values is positive or negative. So that's sort of our goal, right? We want to predict based on two features, x and y, is it positive or negative? So, there's many different models, and so the goal of the learner and the learning process is to find the model that best fits the labeled training data, okay? So in this case, this is our labeled data, and then there's a lot of other points that we've never seen before that are unlabeled, and we want to come up with the best way of capturing this that's likeliest to be accurate for unlabeled data. So let's look at some different models. So hit one. Okay, so a really simple model might be a line. So you could imagine that I just simply start from here to here, draw a line, everything to the left of the line is labeled positive, and to the right of the line is labeled negative. And you can see even this really simple model in this training, it did pretty well. It only had 3 errors, right? This positive was wrong, and there's 3 negatives that are wrong. So it's not bad. It's actually a very simple model, and it does a pretty good job of capturing it. Maybe we want to get a little more complicated. So let's imagine, again, by the way, real machine learning models aren't necessarily shaped like this, although you could imagine a line. And usually it's a lot more than 2 dimensions. But this is just to kind of capture the idea. So let's look at a more complicated one. How about a circle? So let's see what a circle might look like. So more complex might be a circle. So in this case, you have a center and a radius. And as you can see, it did a much better job. There's only one mistake in the training set. Right? Now you hope that the unlabeled examples will map to this real world, so you don't really know until you try it. But at least regarding the training, the circle does a pretty good job of capturing the labeled data, right? And it's much more complex, but there's different parameters. So the line, you got your x and y, and you're starting, your x, y, your slope, and your offset. But in a circle, you have your center and your radius. So each of these different models has different parameters that you can kind of tweak to try to get the minimum error. Okay? Let's look at a more complicated one. Maybe a sinusoidal type thing, right? So maybe it's some kind of weird shape in this space. So in this case, it's just this weird, sinusoidal type shape. And maybe this actually works a lot better. Even though it still has one training error, it seems to do a much better job of separating the positives and negatives than the other ones, right? So different models have different representations and different knobs they can turn. So the learner can be thought of in a simple sense, which learner that you choose, as what kind of knobs you can turn to try to kind of learn and capture your data. So a Bayesian system has different knobs and learners than say, a decision tree, even though it doesn't necessarily map exactly to this space. Fundamentally speaking, you're just trying to come up with some representation mathematically or algorithmically that helps to organize your training data. Okay? This is again, this is just for classification. There are other kinds of learners that are trying to learn different things, but this is sort of a simple way of understanding what a model is. Okay, let's go to the next slide. So let's come up with a really simple toy example to explain this process and actually highlight some of the problems. Before I do this, anyone have any questions so far about the idea of features and models and the basic process? Okay. So in this toy example, let's say we're going to go back to the animals, right? So our definition, let's say we pick a definition of, given an animal, we want to figure out what kind of animal it is, right? Specifically, given a set of predefined animals, we want to classify an unlabeled animal into that set. So we know in advance we're looking for these certain 4 kinds of animals, and we see an unknown animal, we want to know what kind of animal it is, right? What's the likeliest class if it belongs in the set? And more formally, the target might be the probability of each of the different kinds of animals, and the features might be properties of the animal. So in this made-up example, I just spent 2 minutes thinking about it and said, Here are some interesting features. The number of appendages, the dominant skin or fur color. Does the animal have big ears? Does it have a big nose? Is it furry? How much does it weigh? How old is the animal? And so these might be examples of features that might help you to predict, oh, that's a duck because, you know, it weighs this much and it, you know, doesn't have fur or something, right? So let's look ahead, okay? Next slide. So we start off with our labeled data. So in this case, I just picked 3 of the labeled points. So I have a sheep and 2 cows. And then we want to convert them into features that could be used by a learner. So in this case, the first one is example A1. There's no real names. And we know as a human, we've decided as an expert human labeler that it's 100% chance of being a sheep, and it's not a cow, a duck, or a pig. Okay? And you know, it looks like to me, you know, maybe I'm wrong, that it has 4 legs, but actually you can't really see that, so maybe I messed up and thought it only had 2, because in this picture you can't see its hind legs. Its color, well, okay, what does that mean, right? So I just said it's black, because I'll just ignore the fur color, okay? Does it have big ears? Those don't look too big to me, so let's say no. Does it have a big nose? Not as big as the other ones. Is it furry? Yeah, it looks like fur. Okay, now let's look at the second one. It's a cow. Well, what color is it? Well, I don't know. I mean, what does it mean for color? Well, that's kind of important, right? So I'll just say it's brown, okay? And then you can keep going and see, but I know it's a cow, so it's 100% chance of being a cow, and it's none of the others. And again, look at the other cow, and it's, well, what color is that? Well, I don't know. I only have a few choices, so I'll call it white, okay? So hit next button. So even with a simple toy problem, you can clearly see that there's ambiguity with feature definitions, right? That even this simple example, those really simple features, you know, the definition is really important. Because if you ask 10 people, does that sheep have big ears, they might give you 10 different answers, okay? And in fact, maybe someone might not even realize that's a sheep, and they might think, that's not a sheep, that's a cat. I don't know. I mean, they might make a mistake or something. And so it's really important when you're actually doing this process that you have very, very precise, consistent, and clear definitions of your features, right? And even with a simple toy example, you can already see the difficulties, right? And some people might not think that you know, maybe their definition of cow is different, for example. Like, well, that's a real cow, and that's, you know, I don't know, some other animal or something. Who knows? Okay, so let's go to the next one about running the learner. So now we got these examples. Let's run the learner. Okay, model equals my learner training data file. What? Really? It's that simple? No magic? Like, all I take the data, put it to a file, call a function, I get a model? Wow. Actually, that is actually how it often works. And in fact, you know, in terms of the details of different kinds of learners and models and such, that's for another talk. I'm not going to go into detail. But it's important to note that right now in today's society, there are a large number of free or commercial software packages that literally you put your data in a data file and say feature 1, 2, 3, 4, 5, target, say go, and it gives you a model. And in fact, at Quixey, we're using software that does this for us. I did not write, and nobody in this company wrote the actual code to do the modeling. Okay, we're using other code to do that. And you know, for some people, it's come as a surprise. They think there's a lot of complexity in writing custom learners and models. And in reality, there's tons of research out there. There's lots of different choices. Pick one, feed your data in, see how it works, right? And it literally is this simple. Now, maybe it takes a few minutes to run or a few hours if you have a lot of data, but it's not actually complicated to run the learner. The harder part is building up the train data file, defining your problem, and then the next step, which is evaluating. So let's look at the next step. So how do we do in our little example of identifying animals, right? So first thing is, for any applied machine learner, it's really important that you evaluate it correctly. Because the evaluation needs to be specific to your application. You know, for example, maybe I'm building an app search engine, and I want to evaluate it. So I pick, you know, 1,000 random queries, and I see how well I did, and my score is what percentage of those I found the best results for. But what if those 1,000 random queries are asked once versus, you know, what if those queries that, let's say that like half of them are popular and half of them are really rare, and I get every single popular one right and every single rare one wrong. Is that better than getting 80% where I get the unpopular ones right and most of the popular ones wrong? Well, not necessarily, right? So the evaluation is critical, right? Does it matter that, that I didn't recognize the goat as a goat? Maybe it matters, maybe it doesn't. Depends on what you're trying to do, right? So how did we do? Well, for the duck, we gave it a very high probability of being a duck and a low probability of being everything else. For the sheep, we said it was a high chance of a cow. So maybe that's bad, right? I mean, we want to say this is a sheep, definitely not a cow. But our learner in this example, with the made-up system before, said it was a high chance of cow. For a goat, which is not in our set, we thought it was half sheep, half cow. Okay? And you can imagine, a learner might make these mistakes, but these are errors, right? And the last one, for an octopus, we actually got right because we said it was a very low chance of being any of the other animals. But maybe we want to identify octopi. I don't know. So let's look at the next slide. So in a sense, you could argue from these examples we failed, right? We did a very bad job of recognizing these animals. So how do we improve it and what went wrong? Why did we not recognize the octopus, or did it matter, right? Or the goat? Why does the sheep have a high probability of being a cow? And what do we do about it? So when inevitably you're applying a machine learner and you discover it doesn't work the first 50 times around, right? What do? Well, again, as I said before, you repeat each step as needed. So in this case, our formalization did not consider all the animals, right? If we really wanted to recognize goats, maybe we should have included goats in the training set and actually had a probability score for them. Likewise with the octopus. The second thing is maybe our features might not have captured all the subtleties like spots or feathers, right? So maybe goats don't have spots and cows do, and if we added a feature has spots, then maybe we would have known the difference. Maybe, I don't know, right? But also, in this simple toy problem, there were very few training points, right? At least from what you saw. Maybe if we added more examples, the learner would get smarter and have a much more accurate model. So as you can see, you want to look at each of these things, figure out what went wrong, and sort of, take each step and step through it until you end up with a better system, right? And each step presents a place where a mistake can be made. And I'm going to share some stories that are interesting stories that really happen. One might be an urban legend, but most of them I personally have experienced or talked to the people or actually done myself that highlight a lot of things that can go wrong so that you don't make these mistakes. So let's look at the next slide here. Okay? So the first thing is, in my observations in doing this for over 10 years, one of the biggest problems that I've seen that causes problems in applied machine learning is actually coding errors or mistakes with data. You think you've got this great system, you build it, you've got perfect features, perfect definition, and by accident, some programmer messed up when a feature is undefined, and in the training system it's a 0, and in the production system is -1. Or maybe they accidentally take the previous value in the code. And so now all of a sudden you run your learner, it looks good, you apply it and test it, and it sucks because someone made a coding bug or put the wrong code in the wrong place, right? Maybe the definitions of the features may have changed. So we run the learner, we do it, train it, and then we suddenly add the color brown, which we didn't have before, right? And now when we put the data in to evaluate, the color brown comes in, it didn't exist, and it gives bad results, right? Also, sometimes some of these coding errors are very, very subtle and hard to catch. It could be returning a bad value once in a while. And other times, they're completely obvious. So while at SearchMe, it's happened multiple times that we'd go run our little learner on some training data, and the learner would basically say, hey, something's really wrong. It gave a really high error rate, and we couldn't figure it out. We looked at the data, and literally, of the 50 features we had, one of them was 0 every single time. It's like, wait a minute, this really important feature was 0 every single time, something's wrong. And so these kinds of problems are very common. In fact, one of my former coworkers shared a story at a major search engine where they were building handwriting, or a major company actually. They were building a handwriting recognizer, and they were getting mediocre accuracy. And he went through and looked at the features and discovered half of them were programmed wrong. Not half, but several of them were programmed wrong. And when they went and fixed the bugs, all of a sudden the system went from being terrible to being very, very accurate. And so this is something that's not talked about in the literature, but you have to be careful of that. Always check your data. If things look like they're wrong, there probably is something wrong. Okay? So let's continue with some cool other stories. So the first story, I call it complexity. Okay? And so this is about, obviousness, right? So Soman Chakrabarty, who's a friend of mine, a professor at IIT, famous in web search and machine learning, he did a really, really cool experiment. And so what he did for this experiment was he tried to start off by building a simple classifier to predict if a web page belonged in a specific Yahoo category. So he picked a Yahoo category, labeled web pages, and said, yes, these belong, no, they don't, and then basically built a machine learner, made some simple features, ran it on all different kinds of machine learners. So he took like 5, 6 different kinds of learners, ran the learner, got some results, and said, oh, this is interesting. But that's not the cool part. What he did next was really interesting. Remember how I said that you take your examples and you convert them to features, right? So he added a feature that was the answer. Okay? Kind of silly, right? Why would anyone do that? So any human looking at this would be like, oh my gosh, I have the answer, right? It's obvious. But when he ran the learners, each of the different kinds of machine learners on it again, what happened, right? So what did the system do? So let's go to the next slide and see what happened. So any human would learn that the result equals answer feature, right? It's kind of obvious. But different types of learners were actually unable to learn the simple model. Remember when I showed the models and I had a line and a circle and other things, right? They have limitations of what they can capture. And so they might not be able to just simply say input equals output. Like a line or something, maybe, but maybe assign you so I can't do that, right? So different kinds of learners were actually incapable of correctly learning this answer, the output equals the answer, right? And for those who are technical, the learners which are known as able to kind of overfit things like neural networks and Bayesian decision trees, they all got it right, 100% accuracy. And then the actually more popular recently, the support vector machines and the kinds that try to kind of generalize, they did not get 100% accuracy. They actually didn't do that well, even though the answer was given to them. So, right, if you want to know specifics about each learner and why, you can come talk to me afterwards, and I can explain the theory behind them. But that's beyond the scope. Let's go to the next slide here. Right? Okay, so now this may or may not be an urban legend, but there is a lot of evidence to suggest this would be the case. So this story 2 is rats versus humans. Okay? So there's a really simple experiment. You have 2 lights and a button next to each light. And it's sort of a game that you play where there's some pattern that chooses the sequence of which light will light up. Maybe light 1, and then light 2, and then light 2 again, and then light 1. And the idea is you want to push the button to predict before the light lights up, which light will light up, right? Now, for the rats to play the game, they just simply, if you hit the right light, then the rat would get food, and if it was wrong, it wouldn't get food, okay? Some stories say that the rat would get shocked if it was wrong. It doesn't really make a difference. But the point is that you hit the button and you try to figure it out, right? So a rat versus a bunch of graduate students tried to play this game to see who did better. So who won? What happened? Let's take some guesses here. Who thinks the graduate students won the experiment? Who think the rats won the experiment? So clearly there's a lot of people don't put much faith in graduate students doing this game, right?
You didn't give them food.
Well, should give them Red Bull. So, well, now here's a question, right? So if this is what you're doing, and all you know is that you have some history of the sequence of lights in the past, right? That's sort of your training data, right? The pattern of lights. So what would you do, right? Anyone have suggestions? Maybe you'd make a complicated learner and try to figure it out. Okay, Nick, what would you do?
Well, you mean if I were being the predictor?
If you were playing this game, what would you do?
If I didn't see a clear pattern to the lights, I would always predict the one that had come up more often.
Okay, so if you look at this for a while and you notice that one light is more frequent than the other on average, right? Significantly more frequent. There's no obvious pattern. You would just give that answer every time.
Yes.
And that is exactly what the rats did, and that's why they won. But let's go to the next slide. Okay? So in the actual experiment, the lights were programmed to light up 80% of the time light 1, 20% of the time light 2. And the rat really quickly learned just hitting button A every time did pretty well. Now, the graduate students thought there must be some kind of pattern. Let's kind of analyze this data and do complicated learning and figure out some kind of pattern, and then we'll use that to kind of guess what light's going to light up. And you know what? They did worse, because the simple model in this particular case was actually the best, right? Now, but let's look at the next slide. But in this case, it happened. You can go to the next slide. So in this case, it happened to be completely random, or pseudo-random, right? You can imagine a really advanced learner could have learned the random number generator in the computer, but that's kind of unlikely. But what if there actually were a pattern, right? Maybe, for example, it would be 8 times in a row light A, and then 2 times in a row light B, right? So it's the same probability, but now there actually is a pattern, right? So in this case, the rat would still get 80% because the rat wouldn't be able to learn. At least experiments, I was actually doing research on this, that the way that rats play these kind of games, they would probably behave in this way, even if it was 8 and 2 and 8, consistent. They don't have the ability to count like that, right? So they would just keep hitting button A anyway, right? But a human or a good learner might actually learn, hey, I noticed this pattern, right? That 8 and then 2 and then 8 and then 2, and you might get 100% accuracy, right? So the point is that if you have a good model, it can help you if there is something to learn. But if there is nothing to learn, maybe the simple model is the best, right? That the best you're going to get in random is just always give the answer A. But that's also very important because in the real world, even if your data were averaging out in some way, if you set up your learner incorrectly, it may come to this conclusion, even in the case of 8, 2, 8, 2, 8, 2, 8, 2, because if your model can't capture that kind of thing, it may say the minimum error is just giving A all the time, even though there might be a better model. So it's very important that your model be capable of capturing these things. So let's go to the next story. So there's this widely held belief that's actually supported by a lot of theory and been formally proven that more data is better, right? So you remember I said with training data, you want to put lots and lots of training data. The more training data, the more examples you have, the better it's going to be, right? So at SearchMe, we built a machine learned ranker, similar to what we're doing at Quixey, not exactly the same. And the goal is you're given a query and a URL, and we want to predict a relevance score. Fairly straightforward. So we define the problem as, given a query and a URL, let's predict how a score on a fixed scale for this so we can rank web pages. And so we need training data, right? So how do we do it? So we took the queries from the AOL logs, which got leaked, and then they got recalled, and then big disaster. And we took real web search queries, and then we took those queries and sent them to Google, took the results, and then had those labeled. So we used real data. So it's really good training data, right? And then we came up with a bunch of features, which textual features could include things like, frequency of keywords in the document, percentage of words in the query that are in the title. We came up with pretty good, text features, and we trained a model. So what happened? So let's see what happened. At first, when we first ran this, it was a really weird problem. Okay, very, very often, if you type a 2-word query in, the system would favor pages that were home pages that matched exactly one of those words over more relevant pages. So as an example, if the query were general relativity, the General Motors homepage would score higher than a page that's actually about general relativity. It was really strange. It was consistent. And you'd look at the scores, and the model consistently told you that missing a word was actually a good thing. That somehow you've got 2 words in your query, and if one of them matches in the title, it's more relevant than if both of them match in the title, right? That's kind of weird, right? So what happened? Why did this happen, right? We gave it all this great data. We picked real queries. We used real web pages. We labeled it all properly. We checked everything and couldn't figure it out. Well, actually, we could figure it out eventually. But so what happened? So upon further future investigation, real queries had about 14% rate of spelling errors. Okay, and unfortunately on the web, as we've even seen in our app search, right, a lot of queries are misspelled, and that's fine, your system should handle real queries, so let's take real queries. Now, when we sent the misspelled queries to Google, which was our source of training data, they automatically spell corrected it. So you'd have a 2-word query, say Continental Airlines, and it would return the homepage of Continental Airlines, well now United, and you'd get relevant results. So the learner saw a large number of examples where missing a word was more relevant than since we didn't do spell correction. So it saw lots of examples of, hey, I've got this case, I match one word in the title, it's got a perfect score. Here's another case, I match 2 words in the title, oh, that's much less relevant. Because of the misspelling, usually the spam pages are the ones that are correctly matching. And so they get very low score, and the ones that are right got a high score, right? Human says, oh, more relevant for the ones that are wrong. So the learner learned that. It learned, it appears to have learned. Again, not all of these things are directly, you can't necessarily map a model to human understanding trivially, but it appeared to have learned missing a word in the title means more relevant. Wow, okay, that's kind of not good. So how do we fix this? So the solution is remove training data. Wait, what? Hold on. So removing training data is a good thing? Well, in this case, by taking out the spelling errors, it actually significantly improved the accuracy. So here is one of several examples I could give, and if you want to know more, ask me, where more data actually hurt you. And it hurt you because your system was not capable of learning those things. So it learned what you taught it, and it actually weakened the model for the things that it could learn. So the goal is to correctly rank these things, but by giving it real queries that are misspelled, it actually hurt its ability to rank queries that were correctly spelled. And the computer didn't make a mistake. It was a human that did this. And because, like I said, there was no features that captured misspelled words, it learned what it was taught. Missing a word is good. Okay, let's go to the next story here.
We have time for about one more story, so which one would you like?
Well, let's see. So, okay, go to the next one, and I'll tell you. So, okay, here's one of my favorites, okay? This is really, really cool. So if you're going to build a machine learner, can I get 2 stories, please? Okay. So it's really important that you know your data. So there was a professor who, at his university, they decided to enter in this competition for question answering on the web. And they were trying to build a system, a machine learned system that could take any question in natural language, crawl the web, look at web pages, and then come up with an answer for it. Which, this is kind of old school. Everyone thinks they can do that. But they were trying to machine learn extraction functions that could do this, right? So the goal is learn regular expressions that can automatically scan web page to extract answers. So they said, well, okay, now we need to come up with training and testing data. So what do? They go and they take this as an ongoing annual competitions. They took questions and answers from previous years of the competition to use as training data, right? It's already labeled, they know the questions, they know the answers, let's use that. Okay, so let's go to the next slide. So they did this, and the initial results of training were 100% accuracy. Like, no matter how they split up the labeled training and test data, every time it got it exactly perfectly right. It's like, wait a minute. So either they had some great magical discovery for doing web question answering, or there's something wrong. So who thinks that they discovered the secret to question answering? Okay, who thinks there's a problem? Okay, anyone have any guesses of what went wrong? Okay, who doesn't already know the answer? Anyone have any ideas of what went wrong? So remember, the way they set it up is they define their problem, right? We want to take a question, learn an extractor that looks at web pages to figure out which words are the answer. And their training data was previous year's questions, and answers, right? Okay, so what went wrong? Let's see what they did, what happened. So they did a detailed analysis, and they suddenly they realized their system discovered the website of the competition. Okay? And on the website of the competition, it had all the previous year's questions and answers. So their training data and their testing data is trivial, right? You see, oh, domain equals, this domain, right? And, question, exact match, followed by a colon, followed by the answer, right? Really simple. And it's 100% accurate. So, of course, the learner picked this up and it correctly learned exactly what it was taught. And so, it's really easy to learn to extract the answers if they're given right to you. Now, the thing is that this illustrates one of the problems is that a lot of people will run these systems, look at the scores and say, oh, wow, I got a great score, this is perfect. And they won't really delve in deeper because they're kind of stuck in this mindset of using the data that's available and not kind of validating in different ways. And it's really important when you're doing your evaluation, especially if you have results that seem kind of extraordinary, to kind of try different things, look at it in different ways. And if things seem odd, you should double check what's going on. Spend 5 minutes, look at which web pages it uses, and you'll say, oh my God, it learned the rule, domain equals, question site. I think there's a problem, right? Then when they went back and deleted that data so the learner couldn't use it, then they got more reasonable results, which didn't work as well, of course, right? Okay, one more story. And I think this is actually really, really cool that you guys will actually do interesting stuff to play with. Okay, so I call this typical as just a bias. So one of the biggest problems in applied machine learning is biases that we have that we don't even know. Either biases from stuff that we've been taught or other people have done, or just natural biases. For example, everyone in this room at least speaks English, and there's English rules. There's sentences, there's words, etc. Right? So typically, and this is actually my own experimentation, by the way, right? So typically, less so now, but still it's very common when someone says, I'm going to build a text classifier, which is take some text, I want to figure out if it belongs in the category or not. Very well-defined problem, well-studied. What the typical approach is, they'll take all the words that occur and put them in they call a bag of words. So the features are just the words that exist in your text, right? And then traditionally, because certain words in English we all know are useless, like the, of, etc., stop words, they're useless words, so they just take them out because people have found that that just confuses learners and messes up problems, right? Why should we add these things that are all the time there, right? Okay, so it makes it this process makes it the features are very simple, it's very easy to model and very easy to understand and calculate, okay? So now I decided I'm going to go build a homepage classifier, a personal homepage classifier. So my goal is, given a web page, I want to predict, is this web page a personal homepage or not, right? So I decided, you know what, I don't agree with these guys that did it the same way before because there's a little things that I noticed about web pages. So the first thing is, it's arbitrary to exclude stop words. So I said, I'm not going to exclude stop words. Why should I bother? Computers have enough memory. Just let's keep the stop words in there. The second thing is I decided to keep information about the DOM and position information. So the title is not the same as the first sentence is not the same as the link on the bottom, right? So you take a bag of words, the word occurred anywhere, it's equal. But let's separate those out. And then I also basically didn't look at just words. I said, well, let's look at actually combinations of words and sequence, and even sequences of characters that occur in the URL. So I had this really large space of possible features, which sounds impossible, but modern computers can easily do this. When they started doing bag of words, computers were less powerful, so memory was expensive. Nowadays, just throw everything in and let the system go figure it out. So what did I discover when I did this? Let's look at the next slide. So one thing that I did was I took all the features and I figured out how important they were. The computer statistically showed me how important each feature was. And here were some of the most important features. For predicting at the time, I mean, things are a little different now, but still it's generally true. Not having the word the in the title is a very good predictor that it's a personal homepage. Which is kind of funny, right? Very few people, at least when I did the experiment, they would, Eric Glover's homepage. They wouldn't say the official homepage of Ford Motor Company or, some news article that has the in it, right? So missing the word the in the title is a strong positive indicator it's a personal homepage. It's not sufficient because some people would say the homepage of person, right? Not having a link to a privacy policy is also a good feature to predict that it's a personal page because people don't have links to privacy policies, companies do, right? All right, so the important features I discovered demonstrate that these biases that people did in the past, maybe because computers were slower or they had assumptions or they used different kinds of documents, actually limited the ability of a machine learner to operate. Other really cool features besides not having a link to privacy policy, if the URL at the time, commercial pages would often have CGI or ASP in the URL. And personal pages would be more likely to be .html. And another one that literally took me a year to figure out, okay? Like I just could not understand why. I saw the data, it was plain and clear in front of me, and yet I still couldn't understand that the word S in the title or first 20 words was a really important feature predicting if it's a personal page. But there is no word S, right? What is the word S, right? I had no idea where that came from, but every experiment I ran showed very strongly this is a really important feature. In fact, it's so powerful that at the time, and I'll actually show you a demo of this, if you took any query to Google or any engine that did heavy text-based features, and you just simply added the letter S, the word S to the end, it would find personal homepages. Or it'd find personal pages. So if you want to find personal pages about people who like a particular car, you put the car model in, you put S space S, and it would find personal pages at the time. Now engines either ignore S or they're very different in kind of guessing what people want, and the way they rank is less text-based, so it's not as common. But it actually had that phenomenon. So let's see. I mean, first, does anyone, if you think you know why the word S appeared, raise your hand here. So why would the word S be important? Okay, so about half you have a guess. So let's see what really happened. So why the word S, right? By coincidence, both my code and the search engines at the time, they decided that punctuation mapped to a space. So Eric Glover apostrophe S homepage is actually 4 words, right? S being one of them. And even today, on systems that are text-based, you can see this. So for example, if you may, if you look at the related search, no, go back, the related searches on Bing for the query baby pictures S, okay, so let's go click at this. So this is going to go to Bing and look at the related searches because they still use text for doing this. So you'll see these are all, more of them are very personal, right? They're very personal kinds of recommendations, right? So most of the related searches are all for personal things, okay? So now let's go back to the talk, Apple tab to find PowerPoint. Okay. Oh, and by the way, if you just, I'll tell you, if you remove the S, you get things like cute baby pictures, baby picture clip art, like a lot less personal things show up as related searches. Okay. Okay. So we can basically, one more slide, and then, so what are the lessons? So not all features are going to make sense, right? You may get a feature that just seems kind of crazy, and it doesn't necessarily mean that it's bad. And common dogma is not always applicable, i.e. skipping stop words. And something that a lot of people don't even think about is negative features, like missing something, can really help you learn a lot. So knowing what something isn't can help you learn what it is. And a lot of people, they think of positive features and evidence that's positive, but yet features missing are very, very useful. This is the last one, just for something that people to think about, especially if people know a little bit of Chinese. Some of you may say, oh, you're wrong, it's not generally true. We can have a discussion about this. I just want to make a specific point. Afterwards, we can talk about it, and I can explain why it actually is useful. I've actually built Japanese language classifiers, and so I can tell you I know a little bit about this. But basically, some email and spam classifiers, they don't even have the idea of words. Like my friend who used to work for an email spam company said they just take all of the non-letters and numbers out and just concatenate them together to one long string of characters, and they learn on sequence of characters. And that is more effective than looking at words, as you can imagine, because when someone says buy Viagra, they'll be like Vi space Agra or something. So now the words don't make sense, but if you removed all the spaces and look for sequence of characters, it matches a pattern, right? So this arbitrary rule of words is kind of artificial. And an interesting observation is not only is the idea of word boundaries artificial, when you look at pictographic languages like Chinese or the kanji characters, there's some interesting observations that you can make. So if you take the word for salmon in Chinese, it's this little pictograph. I don't know if you can see it. But basically, I don't know how to define what the characters look like. But it's very interesting because you look at the word for salmon and the kanji for fish, you'll notice an interesting pattern. That salmon actually has the same character contained within it as fish. And a few other things that indicate sort of what kind of fish it was historically, in you know, how they looked at what kind of fish it was, which literally means, you know, like ground fish, not ground up, but like earth, dirt, ground. I don't know why they did that, but that's, according to my friend, that's what that means. Maybe I'm wrong. But the point is that, you know, why should you stop at words or letters? Why not actually look inside the letters, you know? Why not actually look deeper? And that's the point, is don't let biases hold you back when you're engineering features. So, you know, that's the basic. You can skip to the very last slide now, which is just a blank slide. So the whole point of all of this is machine learning is actually a very simple, straightforward process, right? You just follow the rules. You define your problem, you figure out your features, you collect your training data, you run your model, which people think is hard, and actually that's the easiest part. You evaluate, which people think is easy, and that's actually the hardest part. And then you feed back and repeat. And there's a lot of oddities and things that, you know, will get in the way, but if you understand the mistakes that other people have made through these stories, then you're less likely to suffer them yourself, or at least catch them sooner. So that's basically the talk. That went longer than expected. And I have negative 15 minutes for questions. Anyone have any basic questions right now about stories? Okay, we have.
So when you were talking about the one where you were building a search engine machine learner and the misspelled queries in your training data were throwing it off, is there some reason why you wouldn't prefer to solve that problem? And what you ended up doing was just removing the misspelled training data. But is there some reason why you wouldn't prefer to just introduce some feature for like number of times something with added distance less than 3?
Okay.
The query word appears
So that's an excellent question. Okay, so one of the unfortunate realities of commercially applied machine learning is that you have tight deadlines and schedules, and you have very limited resources. And certain features are actually very expensive to compute. And so at that point, you know, we had to get a learner out there, and it was really quick to just simply do the first solution. And the second solution may or may not have worked. And spelling errors could be synonymous errors or other reasons too. And the amount of effort it would have taken at the time to say, okay, let's add new features about edit distance of words, it's not clear how you define them, right? Because I have a 3-word query, right? What is the actual feature? Edit distance to the nearest word anywhere in the document? Does that, you know, like how do you map that? It's not obvious how to map that. The better answer is to just say, we'll eventually build a spell corrector and then just feed the correctly spelled stuff in and then be done with it eventually. Although, yes, I mean, a good solution to these kinds of problems is feature engineering. And so one way is, you know, improve the model if your model can't represent it. Another way is more data if that's the problem. In this case, the problem was too much data and bad data. And then another really good solution is actually engineering new features that allow the model to capture that. Because if the model could capture that and was able to recognize these spelling errors, then that would have solved the problem too, right? So that's a very good observation. And so, you know, when you're getting weird results, there's probably a reason. And there's many different ways that you can approach it. And we picked the one that was the least amount of effort. Because to actually build something like that at runtime that could look up words in an index or something, you know, for evaluation is actually really, really expensive. Like to compare a single word to all the other words in the document to know that, hey, it's probably misspelled is non-trivial, right? But for training purposes, you could probably do it and see if that made a difference. And we can talk more offline on how one might approach that. But that's absolutely correct, is that feature engineering is a great way to solve these problems. You get examples that don't work, you create new features that can help capture them, to differentiate, to help the model learn and differentiate between what you want and what you don't. So, okay?